All right, so 12.2 is all about linear regression. So we introduced those in 12.1, and we're just going to dive into a little bit more specificity about those linear regressions. And we're looking at a very, very specific line, and that is the least squares line. Or the least squares linear regression line. So let's talk about this line. This is the line for which the average variation from the data is the smallest. It's also sometimes called the best fit line. You see best fit line used a lot more because it's just less words than least squares linear regression line. And so we denote this as the y hat, and this is equal to b naught plus b1x. So this means nothing to us because these are specific variables. Now b1, the slope, is equal to, give yourself some room here, this is n times the sum of x sub I times y sub I minus parentheses the sum of x sub I times the sum of y sub I all over n times the sum of x sub I squared minus parentheses the sum of x sub I quantity squared. So this should look semi-familiar. This does take a part of that Pearson correlation coefficient R that we were calculating in 12.1, and it's doing that to ensure best fit. That's why it's called the best fit line. And of course, as usual, n is the number of paired data in the sample, x sub I is the ith data value in the explanatory variable, y sub I is the ith value in the response variable, and our y-intercept b naught, this equals the sum of y sub I over n minus b1 times the sum of x sub I over n. So you can't get your y-intercept without your slope, and that's by design to ensure, again, best fit. So these can be done by hand. They're not that much fun to do by hand, but we'll talk about with this example exactly the process you would go through to calculate these things, just in case you're a little fuzzy on your summations. So let's jump into this example here. Find the least squares line for the following data. We're going to use a significance level of 0.05 to determine if there is a significant linear relationship using this line. So let's talk about our n times the sum of x sub I, y sub I. So to do this, make sure you're multiplying each pair. Then add up the results. Then multiply by 8, because there's 8 data values, so our n is 8. If you want the y sub I, this is just add up all the data values for the y's. In this case, the average test score, so this would be x and this would be y. Same thing for the x sub I. Add up all the y values. And then if you're doing x sub I squared, you're going to want to square each x value. Then add them up. And for the x sub I quantity squared, well, this you just square your answer to the sum of x sub I. Makes it nice and simple. So all of these have values, so if you're doing it this way, the n times the sum of x sub I, y sub I should come out to be 10882. Oh, there's an extra 8 in there. 108,882.4. The sum of x sub I of all those is 170. So the square then is just 170 squared, which is 28,900. And the sum of the x sub I squareds should come out to be 30,176. And the sum of the y sub i's should come out to 647.3. So that's how you could do that. We're going to flip to the back here where there's a little bit more space, because luckily so this is continuing example 1. The TI 84s and 83s, they always, luckily enough, use the best fit line or the least squares linear regression line as their linear regression. So that linreg option that we were doing in the last section. So that means that we can punch in our data. So this would be list 1, this would be list 2 into the calculators. And then go down, remember it's stat over to calculate, stat calc, and then it's option 4, linreg ax plus b, and you hit enter twice. And so this tells us y equals ax plus b, and it says a is negative 1.043, rounding off here. This is that b1 from our formula, and b is 103.085. This is that b naught from our formula. So our least squares linear regression line is negative 1.043 x plus 103.085. And we're going to note that the r value it gives us here is negative 0.9775. So that's our best fit linear regression. Now, how we test for significance, remember, it comes from the r value. So I did upload the Pearson correlation coefficient tables, CC tables. Now when you're looking at that table that I uploaded, I reminded you that the degrees of freedom is n minus 2, and then that first column says n in the first column. That is equal to, I wrote capital in here, but it should be little n minus 2. So that's how that table works. I got that from an outside source. So our degrees of freedom is 6. And so the way you look up in that table is you find your 6, and then you go over to your alpha. Our alpha is 0.05. And so make sure you're in the 0.05, and you should see that that score, which is our r sub alpha, is 0.707. I believe it's the middle column is 0.05 or 0.05. And so remember, we look at, for statistical significance, the absolute value of r, is it greater than or equal to r sub alpha? So is the absolute value of negative 0.9775 greater than 0.707? The answer is yes. So we know that there is a significance, or a significant linear relationship. So this is our linear approximation, and then we know that there is a significant linear relationship by looking at the correlation coefficient. And we can also look at that and see, remember, the r getting really, really close to -1 tells us that it's going to be extremely close to a perfect line, and our slope is very close to -1. So that's why we have that very, I almost said high, very low R value, close to -1. So let's talk a little bit more about the least squares line, the properties of it. So the properties of the least square line, of course, they match all the known properties of a regular line, and they do come with some extra requirements when they are being used to predict future values or other values that are not known. So the first requirement that comes along with it is that we do not make any predictions using a regression model if, number one, the data is not linear. Specifically in a scatter plot. So if you plot your data and you see it does not have a linear relationship, remember we talked about the types of relationships we can see in scatter plots in the last section, then you don't make any predictions using it, because it means that you are using a linear approximation for a non-linear thing, and you don't want to do that. Number two, when we don't make predictions, is if the correlation coefficient that's R, is not statistically significant. Now, typically, if you get a scatter plot that is linear, your correlation coefficient should be statistically significant, but there are times when we're talking specifically about weak linear relationships where that can fail, and so that's why we have this caveat in here, is always make sure that you have a statistically significant coefficient. Otherwise, again, you'll have improper predictions. Number three is probably the most important one. You do not make any predictions if you want to predict a value outside of the range of sample data. And again, this one's really important. So your model that you build, that least squares line, it's very good at predicting from your minimum to your maximum in your sample that you have, because that's the data points it used to construct that line. If you go outside of that range, though, who knows what's happening? Because while we could have a linear relationship in that range, outside it could go nonlinear. Right? We could have something that does this, it looks linear, and then all of a sudden it does this. Well, it looks linear here and here, but as soon as we go above, that's nonlinear. And so we only use it to predict where we know it has a linear relationship, specifically a statistically significant linear relationship. So that's one of the more important ones. And then the last one, which is also important, is we don't make any predictions if the population we're predicting about is different than where the sample was taken. So this is different in any way. So if I sample something in San Diego, some statistic I'm concerned about, and I make that data, I use a linear approximation, I cannot predict things that happen in Los Angeles. I cannot predict things that happen in New York. I can't predict things that happen anywhere but in San Diego, because that's where the sample was taken from. So if it satisfies all three of these first conditions, and none of these are met, or all of these are met, then it's only good at predicting things for San Diego. And so that's another really important one. Typically, these two go hand in hand. If you fail a linear scatter plot, you probably don't have a statistically significant R, but sometimes you see corner cases where that's not true. These are the two big ones. You never predict outside your range of your sample, and you never predict somewhere else, whether that be geographic or abstractly different. So whatever you take models for, you do not use it to predict something that has nothing to do with your sample. So we're going to go through some examples, just doing some predictions here. So we're going to use our previous regression, our y hat, that we found, which was negative 1.043 times 6, not times 16, times x, 16 is the first one, plus 103.085. So the first one is 16. We know that we have a statistically significant coefficient because we tested it. We know, well, we don't know, but you can plot this if you put it into your calculator to get your linear regression. You can look at your scatter plot and you'll see that it is linear in nature. And so we are predicting then we don't want to predict outside the data range. Well, 16 is right in that range because we were looking at sample size or schools class sizes, and we started at 15, so 16 is in the range. So all you do is plug in your number. So we do y hat equals negative 1.043 times 16 plus 103.085, and this gives us 86.397, and this is average test score. All right, so what we're saying is for a class size of 16, we predict the average test score to be 86.397. 19, again, falls in the range. So we're just plugging in 19. When we plug in 19, we get 83.268. Again, this is an average test score. So we're saying for a class size of 19, we predict there to be an 83.268. Now if you look at the test scores, you can see that we have 18 and we have 20. And 18 was 85. I'll show you, it's right here. 18 was an 85 average, 20 was 82.7, so we would expect these to be in between when we do 19. And so what we see is an 83.268, so that falls in line. Same thing with 16. 16 is in between 15 and 17, so we would expect our model would predict it to be between 85.3 and 86.2. And we have 86.397, so it's slightly off, and that's because we're coming towards the edge of our range there. We're butting up. The more centralized in the range of your data you are, the more accurate your prediction will be. So let's look at 25 now. 25 still in the range because we go up to at least 29. Yep, we go up to 29. So plugging in 25 into our equation, this gives us 77.01. Again, this is average test score. So we would expect a class size of 25 to have an average of 77. And there's some more analysis that you can do after that. Why would that be lower compared to these? And that comes down to how your sample was taken. And then finally in D with 45, 45 is greater than 29, which is what our max value. So that means we cannot use our model to predict this or to estimate it. In other words, an A, not applicable. It's outside that range. It falls under this third category here, outside the sample data. So always be keeping those things in mind. And there are questions in the homework that are going to have you build models, and they're going to say, can you use this data, or predict this data, this data, this data, this data? Sometimes it's numerical like we did here. Sometimes it's going to say things like, going back to that San Diego example, it's going to say, here's a model that you build with San Diego data. Can you predict something from Illinois? And you have to be aware that no, you cannot. Because your sample is taken in San Diego, you can't predict things for outside of San Diego. So keep an eye out for those. They'll be looking to trick you. So we're going to run through a similar example now. But we're going to look at how we can use a hypothesis test from 12.1 to also determine what's called a good predictor or a good predictive model. So here we have average temperature and then rainfall in inches. So we're going to use significance of level 0.05. They want us to use the following data to make a linear regression model or a linear model. So we're just going to use our linear regression. This will be list 1. This will be list 2. And so we have our linear regression gives us our y hat. A is 0.225. B is negative 15.424. So that's in the calculator. If you're not using the calculator feature, this is your B1 and this is your B0 from our formula for the least squares line. Note that our R value here is 0.8592. So our alpha being 0.05, our degrees of freedom is 10. And so using our Pearson correlation coefficient tables, if you're using the one that I uploaded into Canvas, you should see that our R sub alpha is 0.576. So we go down to 10 and then go over to the 0.05 column, and you should see 0.576. Again, we look at the absolute value of R compared to R sub alpha. And so ours is 0.8592, and that is certainly greater than 0.576. So that means we do have a statistically significant linear relationship. Now notice the slope here though. We have a statistically significant linear relationship, but our slope is not very close to 1, even though it is positive, which means that it is a weak linear relationship in terms of the data spread on your scatter plot, but it is still a significant linear relationship in that all of the data seems to follow that weak relationship. It's not quite as, let's say, spread out as we would expect from a non-significant linear relationship. So at this point the problem's almost done, but let's pause and let's take a look at how we would use a hypothesis test to do the same thing. So you have multiple avenues to solve these problems. So using a hypothesis test, we would be first looking for T sub alpha. T sub alpha is T of 0.05. So that's our critical T score. And we're looking at T sub alpha because this is a one-tail test, because we're looking for a significant positive relationship because we have a positive slope. And so this gives us 1.812. That's just using the inverse T for 0.05. And then our null hypothesis here would be that rho would be less than or equal to 1.812. And our alternative would be that rho is greater than 1.812. Looking like an E there. And so we would calculate our testing t-score. Remember, that's r over the square root of 1 minus r squared over n minus 2. And that comes out to be about 5.311. And so then we would be looking at our t, is it greater than t sub alpha, which it is because it's 5.3 compared to 1.812. And so we would reject our null hypothesis, H naught. And that would tell us that there is a strong positive relationship positive linear relationship between the data, the paired data. So that takes us to exactly where the correlation coefficient result got us as well. So you can test your correlation coefficient, or you can test a hypothesis test versus your critical t-scores. Both of these give us the same result. We have a strong significant linear relationship. We have a strong positive linear relationship. So that tells us that we can be 95% confident because our significance level alpha is 0.05. So we can be 95% confident that we have a good predictor or a good predictive model of rainfall based on temperature but only for temperatures between 75 degrees Fahrenheit up to 90 degrees Fahrenheit. Anything outside that range, because that's the outside of our sample range, is not going to be able to be predicted based on our model. And then, of course, you can be asked to predict certain values and ask if you are allowed to predict certain values, and the homework's going to do some of that. So keep your eye out. You're thinking about those properties of the least squares line when you encounter problems like that. I apologize, this video went a little long. It just didn't make sense to cut it right in the middle of an example.